Suppose natural log of x minus natural log of y equals y minus 4. Where's all my markers at? There they are. I'm looking for dy dx when x equals 4. What do I have to do?
Take the derivative.
Take the derivative. So what's the derivative of natural log of x? Well, what's the derivative of natural log of x? Minus, what's the derivative of natural log of y? 1 over y times, you could say y prime, I'm going to say dy dx because that's the notation that it's in. Doesn't matter. Equals, what's the derivative of y? Dy dx or y prime, and then 0 there. And then we're going to plug in, we're looking for dy dx, so we're just going to plug in these values. It says when y equals 4, then x equals 4. So it's going to be 1 over 4 minus 1 over 4 dy dx equals dy dx. What do I do now? So I got 1/4 equals 5/4 dy dx. All right?
What did you do?
I added 1/4 dy dx. Plus 1 dy dx is, okay. So I'll multiply by 4, so you got 1 equals 5 dy dx. So dy dx equals 1/5. Are we okay with that? What do you want me to do?
The second part.
This.
Yeah, I'd go from that one to the next one.
1/4 minus 1/4 y prime equals y prime. How about this? 1/4 minus 1/4 x equals x. How do you solve for x? Welcome.
That's even better. Oh, yeah.
You're good now?
Yeah.
Okay. What? All right. All right. Okay, number 2. A sphere is expanding in such a way, so you're going to expanding in such a way, the area of any circular cross-section through the sphere's center is increasing at a constant rate of 2 centimeters squared per second. What is that?
A prime.
The area of the circle. Well, what's the area? Area is pi r squared. And a prime is, what does it say? 2?
Yeah, it's
2 centimeters squared per second. Okay. At the instant when the radius of the sphere is 4, so r equals 4 centimeters, what is the rate of change of the sphere's volume? So what are we looking for? V prime. You guys okay with that?
Yeah.
So we've got to figure out what V prime is. Well, I'll give you what V is. So V equals 4/3 pi r cubed. Okay, so what's V prime? Remember, we're taking the derivative in respect to what? No, because we have time here. So it's volume in respect to time. So the derivative is in respect to time. That means volume is a function, and r is also a function, because we're taking the derivative in respect to time, not in respect to r. So what's the derivative of this?
4 pi r squared.
4 pi r squared
Times
times r prime. Are you guys okay with that?
Yeah.
Is that where you went wrong?
No.
No, you did that?
No, everybody thought r prime was 2 because. No, that's r. Because it's the area prime.
It says the area is increasing, right?
Yeah.
Okay, all right. But are we good with this derivative?
Yeah.
Because this is in respect to time, not in respect to r. So now we're looking for this. We got to know these. Any ideas? Do we know those?
Put area, find the derivative of the area.
Take the derivative of the area?
Yeah, to find our prime.
Okay. Oh, all right, fair enough. So A prime is equal to what?
2 pi r.
2 pi r times r prime. And then we could plug in what we know there. So that's 2 equals 2 pi times 4 times r prime. So we got what? Well, 2 equals 8 pi r prime. So r prime equals 1 over 4 pi. So we plug that in there. So 4 pi times, what's r? Okay, so 4 squared times r prime is 1 over 4 pi. And then simplify from there. So v prime equals, that reduces all together. So 16. So the answer is B. Are we okay with that? What is that called? What concept was that? Nobody knows? Related rates? Right? The rate of volume is related to the rate of the radius. You're not taking the volume in respect to r, you're taking the volume in respect to t. So are you guys good with this derivative? Yes? And then we plug in what we know. Well, we know r was 4, but we didn't know what r prime was. So we had to figure out something about r prime. So we took the derivative of a because it gave us something about a prime. Are you guys okay with that derivative? And then we figured out what r prime is so we can plug it in there. Okay. That's that.